Alright, this video is going to be a review of piecewise functions. And the first thing we want to do is go ahead and define a piecewise function. And so piecewise functions are functions that are defined by more than one equation. So a piecewise function is one that has multiple pieces to it, which is why it's called a piecewise. So for our first example, we're going to look at a piecewise function and then we're going to go ahead and do a few things with it. So this piecewise function is going to have three pieces to it. The first is going to be linear, negative x plus 1 if the x values are between negative 1 and positive 1. It's going to be a linear function 2 if the x value is exactly 1. And it's going to be the parabola x squared if x is greater than 1. So the first thing we want to be able to do with the piecewise function is we want to be able to graph it. So I'm going to go ahead and sketch a graph here. So my first is linear. It has a y-intercept of 1. And in front of that, that's a negative 1 over 1 if I was to make that a fraction, so I can see rise over run. So I'm going to go ahead and ignore this part over here, and I'm just going to sketch what I know about this graph. And if you look, I'm doing it kind of lightly because we're not going to use all of this, but I've got that slope of negative 1, and I have a y-intercept of positive 1 right there. So I'm going to go ahead and sketch this just real light. And then here it says we're only using those values if the x value equals negative 1, if it's equal to negative 1, and then all the way up to positive 1 right there. But it can't equal positive 1. And we're using those values in between. So that right there is the only piece of that linear function that we're using. So I'm going to go ahead and erase the rest of it. I don't want any of this. Okay. Next it says f of x equals 2 if x equals exactly 1. F of x is another way of saying y. So they're saying the y value is 2 if x equals 1 exactly. So when x equals 1 exactly, the y value here is 2. If this had been a range of numbers, if it had been like from 1 to 7, then you would have had a horizontal line. Anytime you have y equals a number, that's a horizontal line. And then last we have that parabola, so x squared. So parabolas typically start at 0, 0, and this parabola doesn't have any sort of transformation that tells us it went to the left or right, or that it went up or down, or that it had a stretch or a compression. So I know that this parabola starts at 0. And when I learned about parabolas, they made me learn the pattern for them. So I know that parabolas go over 1, up 1, over 1, up 3, 1, 2, 3, and then over 1, up 5, 1, 2, 3, 4, 5. If you don't know that pattern, that's okay. We can draw a table of values. So we can plug in 0, plug in 1, plug in 2. You could graph it on your calculator to see what it looks like. So you have a few options there. And again, I'm going to go ahead and sketch this real light because I know I'm going to be erasing parts of it. There we go. And here it says we're only using x values that are greater than 1. So on the parabola, here's the x value that's at 1 exactly, and I can't equal it, so I did an open circle. And then anything greater than 1 is going to be this direction. And then I'm going to go ahead and erase the other part. Okay. So that's our piecewise function right there. One of the keywords is function. So when you are finished drawing this, you should be able to do the vertical line test on it, and it should pass the vertical line test, meaning your pencil should not touch more than one point on the graph at a time, because that would mean that you graphed something that wasn't a function. All right. Second, we want to be able to find certain pieces of information about a piecewise function, we want to be able to evaluate them. So we're going to go ahead and evaluate this piecewise function at 4 different points. So I want to see what happens if I plug in -3, if I plug in 0, if I plug in 1, and if I plug in 5. And you can use the piecewise function itself up here to evaluate these numbers, or you can use the graph. So you have 2 options there, and sometimes one makes it easier than the other to see what the correct solution is. So here, if we were to evaluate the function at -3, if you look at the graph, you can see -3 is not even defined. It's over here. And if you look at the piecewise function itself, we can see that in these domain values and these x's that are allowed, -3 is not on that list. So here I'm going to write, if I evaluate at -3, I'm going to find that this function is undefined. There is no value there. Next, if I want to evaluate the function at 0, you can look at the graph and see that when the x value is 0, the y value is 1. Or you can go over here and say, well, 0 is between -1 and 1, so I know that in the function I need to plug it into this one. And -0 plus 1 is just 1. Next, if I plug in 1 exactly, I can see that there are 3 different spots on the graph where I can see x values of 1, but the only time we equal 1 is at that y value of 2. And again, you could have looked up at the function to see that. And then last, if we want to plug in 5, if I try to look on the graph, I'm not going to see that. My graph only went to 3. I have an arrow there, so I know it continues, but I didn't graph it after that. I didn't plot any points. So for this one, I'm going to have to look on here and say that 5 is greater than 1. So I know that I should plug 5 into the quadratic right here. And that means that 5 squared is 25. So if I were to evaluate the function at 5, my y value there would be 25. Some other things that we want to be able to find out about a piecewise function would be the domain and the range. And if you recall, the domain is the allowed x values, and we have those allowed x values written down for us. They're written right here, so that's the domain. So if you look, the very smallest x value that we can have is -1, and that x value there is included. So I'm going to go ahead and put a bracket, because that's what you write when you include numbers in interval notation. And then here it looks like it skips 1, but here we can see that 1 is included. And then here we can see we're using all the numbers greater than 1. So it looks like the domain is from -1 all the way to positive infinity. And if you look at that visually, what you're going to see is that the furthest to the left that the graph goes is -1, and the furthest to the right that the graph goes is this arrow here. So -1 to infinity, and I have no gaps in the middle. For the range, we don't look at the function itself, we actually look at the graph. That's the easiest way to find it. And we're looking from down to up. We're looking at the allowed y values. So the furthest down that the graph goes, the very lowest y value that I can see is 0. And that value is an open circle, so it is not included. And then as I look, I can see I've got these values from 0 to 1 and 1 to 2. And this value looks like it might be skipped, but it's not, because it's the same y value right here. And then it goes up and up and up and up and up, and then I have an arrow. And so I'm going to say that the range for this graph is from 0 to infinity. All right, let's do another example. So here what we're going to do is we're going to write the equation. For a piecewise function. So to start, we'll go ahead and sketch a graph. All right, and to start with, we're going to go to the left 4 and up 1. And that point right there is going to be a vertex for a parabola. So it goes over 1, up 1, over 1, up 3, like so. On this side, go ahead and put an open circle right there. And then right underneath this, we're going to put another open circle here, and we're going to make that go 7 spaces. Or, yeah, we can do 7. 1, 2, 3, 4, 5, 6, 7. Like this. All right. And then from here, we're going to go down 1 over 2, down 1 over 2, like so. Okay. And then right underneath these 2 open circles, we're going to go down here and put a dot right there. So if we look at this piecewise function, we're going to see that I've got 1, 2, 3, 4 pieces. So when I write my function, I can already tell how much it's going to have there. Okay, so the first thing I've got is this parabola. I typically go from left to right. You don't have to. You can mix it all up if you want. So here we have a parabola that has a vertex at -4, +1. So the way that we write that, we have to the left 4, so we're going to put the opposite sign inside the parentheses, and then up 1, so +1. And here, over 1, up 1, over 1, up 3, that's a very typical growth pattern for a parabola. So I'm going to go ahead and leave that there. Now, if I look at the x values that are happening here, I can see that I've got a left arrow, so that means that's infinity. But the x value right here is -2. So I'm going to say that all these x values right here are any x values that are less than -2. So I'm going to say if x is less than -2. All right. Next, I'm going to go ahead and get this little dot right here. So this one is a y value of -1 if the x value is -2 exactly. So I'm going to say a y value of -1 if the x value is -2 exactly. Up here, I have a y value of 1, 2, 3, 4. I have a y value of 4 if the x value is between -2 and +5. So I have a y value of 4 if we have -2. We are not going to include that -2 because that was an open circle. And then the x can be less than or equal to +5. So it was within that range of numbers there. Right? And the reason it's written as a plain number is because that was a horizontal line. Okay, and then last, we're going to look at this linear equation over here. I can see it has a slope of down 1 over 2, so -1 over 2x plus, and I know it has a positive y-intercept somehow. I just have to find the y-intercept. So you can always do it graphically, like I'm doing right now. I'm kind of cheating here. I'm following that up here. Or you could do it algebraically by hand, you know, and pick a point and plug it in. So I can see that it's on either side. That means that my y-intercept must have happened at a halfway point. So I'm going to go ahead and count. 1, 2, 3, 4, 5, 6.5. So plus 6.5. If, and this is only true if the x value is greater than 5. Now you'll notice I did not put, sorry you couldn't see it, I didn't put equal to 5. I can't have equal to 5 in 2 different spots. I can only have it in one. It doesn't matter which one you put it in. So you could put the equal to 5 right here, you could put it down there, it doesn't matter. We just know that these 2 pieces are connected. So somehow this point has to be filled in, and it's got to be filled in by one or the other of those. Okay, so that's that part of it. There's one more thing I want you to put in your notes, and this is just to think about. So we're going to go ahead and draw a picture of an absolute value graph. So absolute value graphs, if you recall, they are perfect V's like this. And the equation for this absolute value graph is it's negative because it's flipped upside down. left 2 down 3, so x plus 2 and then down 3. So that is the equation of the absolute value graph. I want to challenge you to write this, ignore the fact that we know that this is the equation that works for it, and instead I would like you to write a piecewise function for it. And this piecewise function would have 2 pieces, right? So that is the challenge.